Thank you everyone for joining us on Zoom today. We are so happy to have Swee Hong to talk about spanning trees and continued fraction. So I'll give the time to Swee Hong right now.
Okay, thank you so much, Anna, for the introduction. And also, I would like to thank everybody for coming today, especially because of the changes to Zoom. I'm really sorry for the inconvenience. And today's talk is a joint work with Alex Kontorovich. So he is a distinguished professor in Rutgers, also my colleague. Also with Igor, who was my postdoc mentor. He's a professor in UCLA. And we have been collaborating since then. So today talks there are two main characters: spanning trees and continued fractions. Okay, I will start with spanning tree first. So for today, our graph G will always be a finite graph, will always be a simple graph. So this means that there are no loops, no parallel edges. Let me just say that: no loops, no parallel edges. Okay, and a spanning tree is a subset of edges of the graph that is both spanning and a tree. By spanning, I mean that it includes all vertices, and by a tree, I mean that it has no cycle. So for example, let's say G is our graph here. This second picture is a spanning tree. The third picture is not spanning because it doesn't include this vertex. Sorry. And the last picture is not a tree because it has a triangle, which is a cycle. Okay. And here's an example of a spanning tree from real life, from biology. So this is a phylogenetic tree, where the vertices are the species of either a plant or animals. And two vertices are connected if they are directly descendant of one and another. Okay? And there's an apocryphal story that the phylogenetic tree was actually the inspiration behind the name spanning tree. But unfortunately, I cannot find any evidences. So maybe this is just a fun story to tell. But there's no really real evidence to back it up. Okay. But anyway, enough about real life. Let us go back to math. So one of the earliest questions that people ask about spanning trees is that they're asking how many spanning trees can a graph have? Okay, very natural question. And the first answer to this question is Cayley's formula. It was where it was said that the number of spanning trees of a complete graph of n vertices is n to the power of n minus 2. Okay, and despite the name, the first one who actually proved this result is Borchardt in 1860. And in fact, in the Arthur Cayley's paper in 1889, that actually where the Cayley formulas come from, Cayley even cited the Borchardt paper. So Cayley know about this result and also actually cite the result. And what Cayley did is that he generalized his result to many different graphs. For example, he generalized it to the situation where the graph has different degrees. Okay, but for some reason, but probability for like what maybe is this celebrity effect, people nowadays call it Cayley formula instead of Borchardt formula. Okay. And for general graph, the solution is known as the matrix tree theorem, which says that the number of spanning trees of a graph is equal to the determinant of a Laplacian matrix, where the degree, the diagonals is the degree of the graph, the off diagonals are the adjacency matrix, and to get the number of spanning trees, you delete the first row and the first column of the matrix, then compute the determinant. It's guaranteed that the number must be the spanning tree of the number of spanning tree of the graph. Okay. And this theorem was attributed to Kirchhoff in 1847. And interestingly, Kirchhoff paper has no matrix, has no tree. What it does have is that it has a theorem. And the theorem is actually about electrical network. It's about this how to compute the effective conductance for any edges in a network. And with the modern knowledge, it is possible to convert Kirchhoff proof to something that actually becomes what is now known as matrix tree theorem. Unfortunately, the person who actually made this conversion is now lost to history. We don't know who this person is. So which is why we do the second base thing, which is attributing this theorem to Kirchhoff. This is also the reason why you see that the Kirchhoff year is 1847. but the KV formula is 1860 and 1889. This is because both Portrait and KV does not know about Kirchhoff paper, because the Kirchhoff paper doesn't mention spanning tree. Okay. And I'm pretty sure that Kirchhoff himself doesn't know what symmetric theorem is. Anyway, up till here, are there any questions? And sorry if I feel free to stop me anytime today if you have any question. And especially today, my voice is very hoarse. So if you have trouble understanding what I say, feel free to ask me immediately. Everything good so far? Okay, thank you. And let me continue. Okay, so now we know how to count number of spanning trees. It's a result from 150 years ago. Let us move on to results from 50 years ago. And now we are interested in the inverse version of the problem. That's now known in the literature as the Sedlacek problems. Here's how it goes. First is that Gn be the set of all simple graphs with n vertices. And let Tgn the set of number of spanning trees of all possible number of spanning trees of all simple graphs with n vertices. For example, let's take n equal to 4 here. First is that this set always contains number 0, because you can always have a disconnected graph. It has a 0 spanning trees. Then you can have 1 spanning tree when the graph is actually a tree. Okay, that's 1. The next number, you can have 3, where you have a cycle, you have a triangle plus 1 edge. Then you can also have 4. You can also have 4, where you have a square. And let me skip through this first, go to the last one. You can also have 16 when your graph is a complete graph. This is KD formula, n to the power of n minus 2. 4 square is 16. Finally, for the last graph, this is the situation. This is a complete graph minus this one extra vertex. Do you have a question, Joe?
So you don't make a distinction if some of the spanning trees are isomorphic to each other?
Exactly. I don't make a you mean the graph? We do make distinction of the spanning tree. So for example, let me
the cycle there. It has 4 spanning trees, but they're all isomorphic to each other.
That's what you mean. Yes. Yes. Then we consider a label version.
Okay.
Yes.
Thank you.
Thank you. Yes. And the last one, this one has 8 vertices. This is because this is the graph where you exclude this one graph. And the probability for random spanning tree to include that one vertex is 1/2. That's by direct calculation. Therefore, you get that this number is equal to 8.
Can I ask a quick question?
Yes, Indra, please.
Yeah, so but Kirchhoff's matrix tree theorem, that gives the number of non-isomorphic unlabeled spanning trees, right?
They give the number of labeled spanning tree.
Labeled spanning trees, okay.
Labeled spanning tree. So for example, this graph, the square, this is A, B, C, D. Let me put it that way. Then you can have 4 of them. You can have A, B, C, D, A, B, D, C, A, C, B, D, and A, C, D, B. 4 of them. Wait, I think I missed one of them. Sorry. A, B, D, C, A, C, B, D, and then the other one is this one. Actually, let's see. We'll just have a B, C, B. Yes, this one. Does that answer your question, Sandra?
Yes, thank you.
You're welcome. Okay, and actually one more. Since we are discussing an isomorphic graph, this set we actually consider only the numbers. So for example, you can see that to get the number 1, you can also get it from this graph. You can also get it from graph looks like this. Also only have 1 spanning tree because it's a tree, but because we only consider numbers. And in fact, all other non-isomorphic, all other graph or with 4 vertices, I don't draw them, but then because the number of spanning tree will be one of these 6 numbers. Up till here, is the definition clear for TGN? If it's clear, feel free to do this. If not, then do this. Or feel free to unmute and ask question. Okay, good. Thank you. Okay. Here are some basic property of TGN that we will need in this talk. The first one is that TGN is always equal to TGN plus 1. This is because given any graph G, you can add a vertex to be a leaf and then add an edges. This new graph will have the same number of spanning tree as the previous graph. Furthermore, if you take the union of all TGN, you will see that all numbers appear here except for 2. This is because you can take 3 cycle, so you can take n cycle. N cycle always has n number, n many spanning trees. And the reason why 2 is excluded is that the only graph with 2 spanning tree is this graph. It's 2 vertex with parallel edges. But then this graph is not simple, therefore it's excluded. Okay. And so now we are ready to define what's a Sedlacek problem. So Sedlacek is a graph theory from the what is now Czech Republic. Back then it was called Czechoslovakia. He was called as one of the pioneer of graph theory from the country. And Sedlacek was interested in describing the set of spanning tree numbers TGN. He's interested in what is the size of this graph, what is the smallest element, largest element, what is the density of the set. And in particular, he proved the following result. He showed that for n greater than or equal to 3, the size of TGN is bounded from above by n to the power of n minus 2. This is because of Cayley's formula, the number of spanning trees at most n to the power of n minus 2. And bounded from below by n squared. Okay. And as you can see, it's clear that this lower bound is not tight. It's not the best lower bound you can get. And in fact, that's why there's this conjecture, which in particular would imply that this bound should be exponential. That maybe it should be c to the power of m. For some c that is current for now that's for now unknown. And I want to comment that notice that even if this conjecture is true, then it's actually still not a tight conjecture, still not a tight bound, because the upper bound is of the form of e to the power of n log n. So there's an extra factor log n that's missing, even if we can prove this conjecture. But on the other hand, it is understandable that for maybe people from the era, they might want to be a bit more conservative in making the conjecture, because back then the best bound they can prove is n squared. So maybe n log n might be, e to the power of n log n might be a bit ambitious for them back then. Okay. Any question about the problem? Is the problem clear before we move on to the motivation? Okay, good. Let me move on. So here is one of the reasons why people start studying this problem, and the motivation actually comes from the engineering. So in the engineering, it's known that what we call now is the effective conductance and effective resistance of a network can be computed by using number of spanning trees. And therefore, it makes sense that you could imagine that if you are a boss of a company, also if you're an employee of a company, you could have a boss coming in and then say that, hey, Swee Hong, I want to build this certain network. It must have this number of effective conductance, this number of effective resistance. And I want you to build it to be as cheap as possible, right? That's what they only care about. They want it to be something that's as cheap as possible. And in mathematics, this is the same as saying that given a number t, you need to construct a graph G such that the spanning tree number is equal to t, and the number of vertices is as optimal as possible, which is less than equal to c log t. For some constant c that's greater than 1. Okay, or actually also c greater than 0 here. Okay. And notice that the optimal constant here should actually be log t over log t. But as they say in the what do you call that, in the engineering, log t is actually close to infinity, but has never been observed to do so in the application. So for application, usually people just consider log t to be constant. Okay. Okay, and notice that if we can solve this problem, which actually we will, today we will actually solve this problem, then in particular, it will follow that this solution will imply that the number 1 0, 1, 3, 4 up to c to the power of n will appear as will appear inside your set TGN. In particular, this will solve the previous problem from the previous one. Okay? And the philosophy here is that we should first aim to solve the easier problem first. Then once you solve the easier problem, you see that, oh, how about if you take the easier problem, do some modification, see if we can solve the harder problem. That is the philosophy we are going to, that's the philosophy we are going to follow for today. That's what we are going to try to solve for today's talk. Before we move on, are there any questions about the question, about the motivation? Is everything clear? And maybe let me get some water first before, otherwise I might.
Yeah, just a quick question.
Yes, please, Gary.
Yeah, is showing that thing you have in the bottom equivalent to showing a lower bound of Cn different numbers? Can you get that from that?
So can you say again?
I guess your goal was to show that the lower bound is C to the n. But that statement at the bottom doesn't immediately imply that unless you get something else.
Yes, actually, let me actually have yes. Our proof actually gives something even stronger. We can actually show that almost all number of let's see this. So the goal is that we want to show, in fact, we want to show that there is a c to the power of n here, right? What we can show is that actually almost all numbers with all numbers with density 1 appears in this set. So that's actually
I see a dot 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 means most numbers. So you get your
numbers. Yes.
Okay, got you. Okay. Thank you.
You're welcome. Any other question? Thank you so much for the clarification. Okay, if there are no questions, let me continue. Okay, so let me review what was known so far about this problem. And I will just skip through some of the bounds from the 60s to 2014. The first superpolynomial other-world bound was proved 11 years ago by Azariza, where he showed that TGN has a sub-exponential growth, where it is equal to e to the power of square root n log n. And between Azariza and Song, there are also some work. Let me also skip them. I'm pretty sorry. This is to save time. But the best lower bound prior to our work was Song in 2022, where the lower bound is e to the power of n over 2 term. And his proof is very beautiful. He used this Dirichlet number theory, Dirichlet number theorem to prove this result. Okay. And I will present our lower bound in the next 2 slides. But before I do that, let me move on to the Sedlacek's second problem. So Sedlacek actually gives 3 problems. So today we'll discuss only the first 2. The third one, if we have time at the end, I will discuss what is the third problem. But here's the second problem. It's the same as the first problem, except that now you add the word that you restrict only to planar graph. Okay. Now, for people of our generation, or maybe at least for people from my generation, it might seem a bit strange. Why do we want to restrict the problem to planar graph? However, I was informed that we should think about what was going on in that year 1966. Back then, the 4-color theorem was still open problem. So it makes sense for all graph theories. Whenever they work on the new problem, the planar graph was always at the back of their mind. For example, there's the famous chromatic polynomial. It was constructed by Birkhoff in the year 1929. And the original goal for the Birkhoff is actually to use this to prove 4-color theorem. Of course, in the end, the 4-color theorem was proved by using some other method, but the chromatic polynomial itself arguably become even more important than the 4-color theorem because it connects graph theory to many other fields in mathematics. Okay, so it's the same situation here. That's the reason why Sedlacek is interested, at least one of the reasons. The second reason why Sedlacek is interested is that if you add the assumption that the graph is planar, notice the number of spanning tree is at most 2 to the power of number of edges because it's always a subset of edges. And remember that by Euler formula, E should always be equal less than 3v minus 6. And here n is equal to v, so I forgot to say this, n is equal to v. And therefore it follows that TPN is bounded from above by 8 to the power of n. Okay, So this gives an exponential upper bound for the number of spanning trees for planar graphs. For the yes. And the best bound prior to our work for the upper bound was due to Musin and Schultz in 2010, where they improved it to the point of 5.2852 to the power of n. And the lower bound is again due to Stong, which is e to the power of n to the third, and this is because all the lower bounds that appears in all the graph that is used by Stong is also a planar graph. So it does transfer immediately for both Sedlacek first problem and Sedlacek second problem. This is what was known so far about this problem. Are there any questions before we continue? Okay. Yes. Okay, so they have no question. Then let me just without further delay. Here is our first main result. Together, sorry, got too excited. Here is our first main result. Together with my co-author Alex Kontorovich and Igor, we proved the first exponential lower bound for the Sedlacek second problem. We saw that TPN is bounded from below by this number 1.1103 to the power of n. So this gives an optimal lower bound for the Sedlacek second problem up to a constant. So this basically solves the problem. Furthermore, remember by definition, all planar graphs is also a general graph. So in particular, you have TGN is greater than TPN. So it follows that TGN is also bounded from below by 1.1103 to the power of n. And this gives the first exponential lower bound. The first exponential lower bound for the Sedlacek first problem. This is our first main result. Any question about the result itself? Good. Okay, if there are no questions from the audience, let me ask a question to myself. Remember previously that our motivation for studying Sedlacek problem is to answer the question from engineering. Now that we have answer to the Sedlacek problem, let us see if we can also answer the question from the engineering. And it turns out that yes, we can, in the following sense. So recall that the engineering problem is that given a number t, we are going to construct a graph G such that the number of spanning tree of G is equal to t, and number of vertices is at most c log t, so that is as small as possible. And what we can show is that this problem can be solved, we can actually solve this problem for a set of integers t of density 1, where we say that a set S, which is contained in N, this set is of density 1. If we take the limit of n goes to big N goes to infinity, take the intersection of this set with number 1 to 3 up to n, divided by n, this size should go to 1 as n goes to infinity. This is what we mean that this set has actually density 1. This is our second main result. And in particular, it follows that the first main result that we saw from the previous slide, the exponential lower bound, will follow from the second main result. Up till here, are there any questions?
Sorry, I just need a second. Yeah, little t of G is what?
Little t of G. What is the little t? This is the number of spanning trees.
But then it's so why is little t of G equal to capital T? So is T a set of integers of density 1?
It's a number. So it's we want to construct a graph that number of spanning trees is equal to that number. So let's say T is equal to 5. We want to
so with capital T is in a set of, just in your theorem statement, you say for a set of integers T.
I see. This is a set of integers S of density 1.
Yeah.
There exists a planar graph with TGT and T is contained in S.
Okay, yeah, all right. Thank you.
Thank you so much for clarification. Yeah, this is problem with my English. I blame it on my my English teacher.
Swee Hong, I think you've made your statement too weak.
Yes.
I don't think you want to say that T of G is NS. You just want to say that that for any T in S, There is a graph whose number of spanning trees is exactly that t.
Yes, exactly. So, or maybe, yes, exactly. Thanks, Peter, for clarification. Maybe let me say, let S be the set of T such that this is true. Then set S has density 1. That is the statement. Yes. Thanks, Peter, for fixing my mistake. And now this is a mathematical mistake, so I cannot blame my English teacher now. Thank you so much, Peter. Any other question? Any other mistake people want to point out before we continue? Okay. It seems like everybody's happy. So then let me continue to how we solve this problem. And the way we solve this problem is basically that we find a connection to the continued fraction. So this is why the title, this is where the second main characters come in. And recall that for positive integers a1, a2 up to ak, a continued fraction is this expansion, is this number where we write is equal to 1 over a1 plus 1 over a2 plus 1 over a3 up to 1 over ak. And usually some people also add there's an a0 in front of this, so usually there's an a0. But for today, we'll just always assume that a0 is equal to 1. Sorry, a0 equals to 0. This is just to simplify the notation. Okay? And it's well known that every rational number can be written essentially as a unique finite continued fraction by using Euclidean algorithm. And all of the numbers that appear in here, the a1, a2 up to ak, is the quotient that appear in the Euclidean algorithms. Okay. In particular, this means that the length of k is at most a log of u, because that is the length of that's the worst runtime for Euclidean algorithm. And here phi is I forgot to say, this is the golden ratio. 1 plus square root of 5 divided by 2. Okay. Now, here is how we connect the problem from a problem in about the spanning tree to continued fraction. We do the following construction. The input is the numbers b1, b2 up to bl, all of them positive integer. We want to build a planar graph G and edges E such that the ratio of the Tg minus E and Tg over E, G minus E is the graph division, G over E is the graph contraction. This ratio must be equal to the alternating continued fraction of b1, 1, b2, 1 up to bl1. So the even part is always equal to 1. We want these two numbers, Tg minus and Tg over E, to be coprime. This is so that if we can get the continued fraction, we can recover the two numbers Tg minus E and Tg over E. And we also want this graph to be small. So the number of vertices is equal to b1 plus b2 up to bl plus 2. We want to construct such a graph. And in fact, the construction is so simple that I can present it in one slide. Okay. Ready for the graph? The graph is the following. Take the joint of L many cycles. First cycle is B1 plus 2, then B2 plus 2, B3 plus 2, up to BL plus 2. We call this the Sedlacek graph. And notice that because BI is always greater than or equal to 1, BI plus 2 is always greater than or equal to 3. So you never form you never have a non-simple graphs. Sorry. This is the construction that gives us the connection between spanning tree and continued fraction. And here I just want to make a comment, which is that I want to remark that we are not the first people who noticed that this is the graph that you need to use to actually solve the Sedlacek problem. In fact, there are many other authors before us that has even worked on not just this graph, but for even a more general family of graphs. But the reason why they all fail is because they all try to only keep track of number of spanning trees. And because of that, the calculation quickly become too difficult. Then they become less, approach is less, is suboptimal. Therefore, they cannot get a result like our result. In a way, I would say that our innovation here, I think that we are the first people who actually try to keep track of both Tg minus E and Tg over E at the same time as the continued fraction. That I think is our maybe I'd say maybe a little bit small innovation. And the reason why we do so is actually because we have other projects. We have an inspiration from graph theory, where we already know that if you can write matrix theory, where we know that if we can express the problem as a continuous fraction, then it is possible to use tools from a number theory. So I sell my soul now number theory to solve this problem. So we can use tools in number theory to solve this problem. Those tools are developed by number theorists to solve another conjecture that is now known as the Zaremba's conjecture. So we are going to do number theory now, but before we do that, are there any questions about the graph part? Any question about the combinatoric part before we move on? Before I sell my solo number theories.
So can you improve what you said in the previous slide, but or not so much improve, but for planar graphs in particular kinds? So one of the very pretty results of planar graph theory is that planar three-connected graphs are the graphs of convex three-dimensional polyhedra in three space. So,
that is
one might be interested in studying some of these questions for other particular types of planar graphs.
Yes, that's a very good question. The answer is yes. In fact, so actually, I don't know how much I can say here, but actually, just last week, I got an email from Noga. Let's see, where's there's this is the upcoming work by Alon Matiak-Buchik and Lior Gispoliner in 2025 plus. It will most likely come up, it will mostly go up in archive soon, if not already there. That they use our method, they modify it with some very clever idea on experimental combinatorics to show that you can do, the answer is yes. The yes to your question for K-regular planar graphs.
It is on archive, by the way, already.
It's on archive now already? Okay,
Yeah.
great. Okay, then then I don't feel bad. I don't feel bad for for saying that now. For like what do you call that? Snitching out for the results. Yes. And I can say a little bit more about what they mean. That what they do is that they use our construction. They and then they do this blow up for any vertex. They do this what do you call this? Pigeonhole principle, so that all of the graph has a degree 2 or degree 3. And then for everything that's a degree 2, you attach some other new graph to make it a degree 3. That was more or less the proof. Yes, any other question? Thanks for all the great questions today. Okay. If there are no questions, then let me continue. To Zaremba's conjecture, to number theory. So here is the conjecture. sorry for this interruption. This is the conjecture of 1972. It says that for every positive integer u, there always exists a coprime t that is less than u, such that the continuate fraction expansion of t over u, all of the fractions should be less than equal to 5. And the reason why this is 5 is because they check it for 4. They find the contact example when if you change it to 4. This is when u is equal to 54. And for the last 50 years, nobody has found the contact example for 5. And I'm sure that if somebody find the contact example for 5, what they will do next is that they will conjecture it for 6. Okay. So so far, and so far, nobody has been able to prove this result for the nobody has been able to prove this for 50 years. And but notice that in particular, if this conjecture is true, then the sum of A1 to AK will be less than 5 log Q by a Euclidean algorithm. And this will be important. This will be important in maybe at the last part of our talk. Okay. And okay, let me just move on quickly. So for the Sorry. So for a very long time, there's zero progress, no progress at all for this theorem, until finally it was in the year 2015, Zaremba and Alex Kontorovich, this is the same one, my co-author, they make a big breakthrough where they create a method that's called the orbital circle method, where they show that, again, this one is to be changed. This is like the set. For all set, there exists a set of density 1, so that all numbers that appears there satisfy this property, that all numbers is less than, that all quotients of the partial fractions is less than 50. Okay? That is what they proved in 2014. And in 2015, Huang, a student of Alex Kontorovich, improved the bound from 50 to 5. And that is the current best known result for the Zaremba's conjecture. Okay. And when I first learned about this result, I think that this is exactly what is needed to prove our problem, to prove Sedlacek problem. I discussed this with Igor, I discussed with Alex. All three of us agree that this is the way to go. This is how we should solve this problem. And at first, we are trying very hard to improve our third-form graph construction. We try to improve the combinatoric part so that we remove the condition that the string must be alternating. However, after several discussions, 3 of them or 4 of them, we realized that it turns out the number theory has already progressed so far that they're already so advanced, or are they advanced enough that just by using the tool as a black box is already enough to solve the whole problem. And in the sense that we can prove the following things. Change the continuous fraction that appear in the PK theorem from the normal continuous fraction to the one where the number alternates with 1. So this is the one that appears in one graph. That even with this restriction, the density 1 conclusion is still true. And the only price we need to pay is that this number need to increase from 50, is increase from 5 to 110. So we are lucky that so we are lucky that for Sedlacek problem, he doesn't ask for the constant. If we ask for constant 5, then we can do nothing. But because he doesn't ask for a number, then yeah, we can put any number there and we are still happy. This, ladies and gentlemen, is exactly what we need. That with this theorem is enough that we can now use this to solve the Sedlacek problem. We can use it to solve the inverse counting problem. Okay. Any question? And I'm sorry again for all this coughing interruption. Okay. No question. If there are no questions, then let me continue. Okay. Now let me just quickly use this alternating BK theorem to solve our inverse counting problem. Remember, the goal is that given an integer t, we have to construct a graph G with spanning tree number equal to t and number of vertices less than 56 log t. Here, here is our construction that works 99% of the time, or it works with probability 1 as n goes to infinity. Also, as t goes to infinity. It goes like this. First, for all integer u, first you have given any t, you go through a for loop. You go through all integer t that's between t and 110 that is co-prime to t. You compute the continuous fraction. If the continuous fraction is not of the form of the alternating form, then do nothing, you reject. But if it's of the alternating form, then you just construct a sigmoid graph, and by definition, by construction, the number of spanning tree of G minus E will be equal to T, and number of vertices will be less than equal to 56 log T. If this is the case, then we are in business. We'll take our graph G minus E as our output. We are done. And our theorem, our alternating BK theorem, guarantees that our theorem works 99% of the time. And in fact, it might still work even for the other 1%. It's just that we cannot guarantee that for now. I personally believe that it still works for the other 1% because I think this alternating Zaremba is true, where you ask it instead of for integer integer with the density 1, you ask it for all integer t. And maybe the constant you put here will not be 110. It might be 1 million, it might be 1 trillion, it might be very big constant, but this is probably true. Just that we don't know how to prove that. Okay? If this is true, then we should be able, in fact, it will follow immediately that the whole inverse counting problem can be solved deterministically. Then we don't need to do probabilistic construction anymore. Okay. I better just one funny thing I learned. Actually, I told this result to an engineering professor that I know from my undergrad time. I told him that this result worked 99% of the time, and he told me like, oh, that's good, Swee Hong. Then, if that's the case, then I consider this problem solved. Because for application, 99% is good enough. The other 1% you can exclude for them. That is what the engineering people think whenever they have the result like this from the mathematics. Okay. Any question? Everybody happy? Peter, do you have a question? Okay. Yeah. Okay, if there are no question, let me just get some water first before I continue. Okay, if there are no question, then let me just give a very quick sketch of proof of both the original Beaker theorem and the alternating Beaker theorem. Okay, and to prove the original Beaker theorem, we actually need to now switch from number theory to fractal geometry. So consider the following set of fractals, where this is a set of all real numbers, such that all of the coordinate fraction expansion, the numbers is less than A. Okay, so here's how it works. Notice that saying that the number A1 is less than A1 equal to 1 is the same as saying that your number is between 1/2 and 1. So this is let's see, A1 equal to 1. A1 equal to 2 is the same as saying that your number is inside this interval between 1/3 and 1/2. A1 greater than equal to 3 is the same as saying that your number belong to 0 to 1/3. So setting that A1 is less than A, let's say A equal to 2, is the same as excluding this 1/3 of your real number. Now you do the same thing again for A2, A3, A4, and so on. That's the same as removing the 1/3 for every new part that you have. And if you keep doing so again and again and again, in the end, you will remove all things just like with the Cantor set. You will get a set of fractals of Lebesgue measure 0. And the idea here is that the larger the set is, the more likely for the BK theorem to be true. And of course, in order to say for this set to be larger, we need to define some measure. And Lebesgue measure is not good, because in Lebesgue measure, all fractals has Lebesgue measure 0. And turns out the right way to do so, to measure this thing, is called the Hausdorff dimension. It's defined as follows: is that given subset of real number, you define Hausdorff measure as a generalization of the Lebesgue measure. So you define it in terms of the open cover of the set S, except that you add an extra parameter D to actually blow up the measure. In the following sense, when D is equal to 1, this is just a Lebesgue measure. When D is become larger and larger, these numbers become smaller and smaller, and therefore, as for D large enough, the Hausdorff dimension is equal to 0. On the other hand, when D is very, very small, it goes closer and closer to 0, this number, the sum, goes up to infinity. Okay, so Hausdorff dimension is the smallest smallest real number D, so that the Hausdorff dimension is equal to 0. So this is the time when this thing becomes non-trivial. And it follows from calculation that for CA, for the Cantor fractals, the Hausdorff dimension is always strictly between 0 and 1. And furthermore, the dimension converges to 1 as A goes to infinity. This follows just from a direct calculation. And here is the how Kontorovich solves this problem. They have this Black-Box methods that now we call the orbital circle method. What it says is that the conclusion of Beaker theorem actually is a universal result. It's a result as you can get, as long as the Hausdorff dimension of the Cantor set of Cantor fractal is greater than a certain number of 0.984. And this theorem is very useful because it converts the problem of solving the Zaremba's conjecture to the problem of computing Hausdorff dimension. And the computing Hausdorff dimension recently is very easy now because people have developed a lot of algorithms, developed a lot of software to compute this number very efficiently. And in fact, that's exactly what Borger and Kontorovich did. They use computers to compute that this number is for A equal to 50 is equal to 0.986. This is greater than 0.984, and in particular, that's how they prove the original BPK theorem. Okay, with the constant 50. Before I continue further, are there any questions about the Borger-Kontorovich theorem? Everything good so far? Okay, and since then, 10 years later, since there are 10 years between now and the original BK, since then there are already a lot of improvement made for the BK theorem, both on the orbital circle method and on computing Hausdorff dimension. On the orbital circle method, the current best result is due to Khan, which shows that the constant you need to use this orbital circle method has now become 0.7749. Okay, so it becomes smaller and smaller. And maybe if give like 5 years later, maybe I think they will make it even smaller again, maybe to 0.6. Okay. And on the Hausdorff dimension side, the current state of the art is due to Polycott and Vidnova in 2022, where they developed a very efficient algorithm to compute the Hausdorff dimension of any fractals. And in particular, by using their method, they can compute the first 100 digit of the C5, and they compute it in less than 1 hour. Here is the constant they compute. In particular, combined with the previous improvement by Huang, you get that this number is greater than 0.83. That's how you get the current best result for Zaremba's conjecture. And this is where it currently stands. What field here? Are there any questions? No question? Everything good? Okay, if there are no questions, then let me go down to alternating Baker theorem. And for the alternating Baker theorem, the approach is the same. First, you define the fractal, which is now what we call the Hansen-Turek fractal. The one that corresponds to our problem is the one that alternates with B1, 1, B2, 1, and so on. And based on Kant's result, we are in business if we can show that this number is greater than 0.7749. Okay? And this is where we are doing basically a gamble. That if an A exists such that this number is greater than 0.7749, then we get everything. Everything we know about this problem is solved. If such an A does not exist, if this dimension is smaller than this number, then all our effort is wasted. We get nothing. So this is an all or nothing gamble. Okay, so let us roll the gacha, let us roll the dice, see what comes up with this gamble. And fortunately for us, the luck is on our side by a margin of 0.0001. That this number is greater than this whole thing is true, the whole method works, we get our alternating Baker theorem. This, ladies and gentlemen, is our second main result. And I would say that actually maybe our I would say that the main contribution here is the luck, that we are very lucky that all the numbers just happen to match, all improvements just happen to occur before us. Let's say that if you try the same method, let's say just 5 years ago, we can do nothing, literally zero. Okay, and one more thing. So 2 weeks ago, Polycott uploaded a note in archive, show that our calculation, so we only calculate the first 3 digits, and turns out that he said that our calculation is not efficient enough. So by using his better implementation, he can compute the first 20 digits, and it showed that turns out 109 is already enough. 1110 is a bit of overkill. Okay, and that is the current state of the art for the density 1 result of the version of the result. Up till here, are there any questions? Okay, no question. If no question, then let me maybe end the talk by just giving 2 open problems. The first open problem is that ask the Sedlacek, our result give the first known lower bound of the form exponential lower bound. So 1.1103 to the power of n. And I strongly believe that our lower bound is not tight. The right answer should be 2 to some constant of n log n. So notice that if this is true, then this actually matches with the Sedlacek first prop, with the upper bound, with the trivial upper bound, which is coming from the KV formula. I strongly believe this result is true, but unfortunately, our method is very much focused on planar graph. So there's no way our method will work. So to solve this problem, we really need a new graph construction. We really need somebody smart come in and give a new idea. That's the first open problem. The second open problem is that for the second problem, for the planar graph, we now know that this TPN is between 1.11 and 5 to 5.28 to the power of n. We can I'm not so sure, but it's natural to maybe ask, like, maybe does this constant actually converges to a constant c, this exponent? And if this constant c converges, then this constant must be between 1.11 and 5.28. And I strongly believe if this is true, that this 1.11 is not optimal. In fact, as I mentioned before, Alan Buchik and Gisvoliner already uploaded a new proof, improved proof of our method, showing that the lower bound can be actually 1.4 to the power of n. And I believe that actually, even in their paper, they say that their method is actually not very optimal. Definitely, this bound can improve. Exactly to how much, I don't know. But definitely, there is a room for improvement. And let me just say one more thing is that what this Noga and the other two co-authors, Alon, Buchik, and Gisvoliner did is that they took our combinatorial analysis, they find a very beautiful lemma, a very simple but very slick lemma that actually removes the Zaremba's conjecture from the equation. That they can do it directly without using the whole power of Zaremba's conjecture. You will still need the Zaremba conjecture if you want to get a density 1 version. But if you only ask for the number of the size of TPN, then you don't need Zaremba. You can just do it without the by some very smart combinatorics. It's a very beautiful. I strongly recommend reading that paper. Okay, and I think that is all I want to say. Thank you so much for your attention, and I'm very sorry for all this carving instruction.
Thank you so much, Zaremba. Very nice talk. Any question?
So, Swee Hong, this is great stuff. Thank you very much.
Thank you so much, Peter.
Just you mentioned that Zaremba's conjecture is tight because of this U equals 54 example. But when you're looking at sets of density 1 instead of all integers, presumably you could do much better. For example, maybe all you need is 1s and 2s.
That's a good question. In fact, there's also one of there's also one Zaremba actually make he didn't say exactly the continuous state. He make like many conjecture. One of them is exactly that, which is that for n, which is that a bit weaker, which is that for u large enough, you can find a t such that either this is 2, and then you change like a integer u large enough integer u. And I would say that part of the push to actually improve this this bound, where is this? All of this work here, let me go. All of this work here on this improvement to make this corner smaller is to get that result for density 1, for a greater than or equal to 2. And I think that there's a limit that I think 2 is probably not enough. I think 2 is probably cannot be approached by this method because of some technical reason.
How about
3 is the maximum.
How about for the alternating case?
Both of them we conjecture. Even for alternating, I think 2 is enough. But then no. Well, I want to say no, nobody knows. But this group of people, they are working very hard. Every year they make an improvement to this number. So maybe one day. I would say that the limit for this method is 0.5. That is the natural boundary. So maybe one day they will get there.
Very good. Thank you again.
You're welcome.